Welcome, Mr. Sutton here, bringing you the AB Calculus Derivative Extra Practice number 9 solutions. On this problem, to take the derivative, I need to use the chain rule. My outer function is something to the third power. That's what's going on here. So that outer derivative is going to be 3 times something to the second. So 3 times sine squared of 5x squared. The next function in is the sine function. I've got sine of something. So the derivative of that's going to be cosine of something, cosine of 5x squared. Finally, multiplying by the derivative of that innermost function, we have 10x. To make our lives easier on this problem, before we try taking the derivative, I'm actually going to split this up. So I'm going to have ln of x plus ln of radical 3, because multiplication turns into addition when I use my log rules. Ln of 3, radical 3, the good news is this is a constant, so the derivative of this thing here is going to be 0. So we really just need the derivative of ln of x, which is just 1 over x. For this problem, to take the derivative, I notice that I have a variable in the base and the exponent. So this calls for logarithmic differentiation. I'm going to take the ln of both sides. So I've got ln of y, and ln of the right side is going to pop out that exponent with the variable. So I'm going to have an arctan of x down on the ground level, times the ln of the base x. So I'm going to implicitly differentiate everything now. On the left side, I've got 1 over y, dy over dx, because we're taking the derivative of y, which is a function of x. It's an inner hidden function. And then on the right side, we have the product rule we're going to use. So that's the box and ribbon. We've got arctan of x and ln of x, and the derivatives of those, which are 1 over x squared and 1 over x. Multiplying that out with the ribbon, we've got ln of x over x squared plus 1. And then going the other direction, this is going to be arctan over x. And then to get dy over dx by itself, we just multiply by y. So that's going to be y times all of the stuff on the right side in a big parentheses. Now, you didn't have to express this in terms of x, but if you wanted to, you could replace this y down here with x arctan of x. And here's another way of writing the answer. For this problem, at first glance, it looks like we're dealing with a chain rule of sorts. But before we bother with this exponent, let's pop it out in front of the ln, because this is one of our log rules, right? The pop out rule. So we can write this as 3 ln of cosine of x plus sine of x. That'll save us a little bit of a chain rule here. And now I'm just doing 3 times ln of something. I still have a little bit of a chain rule, but not as much of one. So this is going to be 3 over the something, using the ln rule on the outer function here. So that's going to be 3 over cosine of x, sine of x, times, now we have to take the derivative of the inner function. So that's going to be, for cosine, we've got negative sine of x. For sine of x, we've got cosine of x, and that's about as good as it gets. On this problem, to make my life easier, I'm going to split this up using log rules. So I'm going to turn division into subtraction of logarithms by writing ln of e to the x minus ln of e to the x minus 1. And I can simplify a little bit here. This ln of e to the x, the ln and the e cancel, so this is really just x over here. All right, time to stop putting off the calculus. Let's go ahead and take some derivatives. Derivative of x is just 1, so that's pretty nice. For this one, we have a chain rule here. We have ln of something as the outer function. So the derivative of that is going to be the 1 over the something, 1 over e to the x minus 1, times the derivative of e to the x minus 1, which is just e to the x. On this problem, I'm going to have to use the chain rule to take this derivative. My outer function is arcsecant of something. So the derivative of that's going to be 1 over the absolute value of the something, of ln of x, times the square root of something squared, ln of x squared, minus 1. So that's the outer function. Now we have to take the derivative of the inner function of ln of x, and that's just going to be 1 over x, so we can multiply by that. For this problem, we're doing a chain rule. We have the outer function ln of something. Derivative of that is going to be 1 over the something, 1 over arcsecant of x. But now I have to multiply by the derivative of the something. Derivative of arcsecant of x is just 1 over absolute value of x times the square root of x squared minus 1. For this problem, we're going to need the chain rule to take this derivative. Outer function is 3 cotan of something. So the derivative of that's going to be negative 3 cosecant squared of something, the something being another cosecant of x. Now we have to actually take the derivative of this inner cosecant of x, which is going to be negative cosecant of x cotan of x. On this function, taking the derivative requires the use of the chain rule. My outer function is 3 to the something. Derivative of that is going to be 3 to the something ln of 3, so 3 to the arctan 3x ln of 3. Now we're multiplying by the derivative of arctan of 3x. Well, that's going to be arctan of something's derivative. That's 1 over something squared plus 1, so 1 over 3x quantity squared plus 1. Finally, we multiply by the derivative of 3x, the innermost function, and that derivative is just going to give us a tail of 3. For this problem, taking the derivative looks like it's going to be a big mess with that function inside the exponent. I mean, we've got a product rule, then we have a chain rule with chain rules built into it, but we can make our lives a little bit easier. Secant squared and tan squared are part of a Pythagorean identity. We have the identity 1 plus tan squared equals secant squared, which means that I can write secant squared minus tan squared equals 1, which means that this exponent is really just a big 1. So we have x times e to the 1. Now this is really nice because if I'm taking the derivative of x times a constant, I know by the line rule that my derivative is just going to be the constant. So the derivative of this thing is just going to end up being e. To find the derivative on this equation, since I can't isolate y, I have to use implicit differentiation by treating y as a hidden inner function of x. So whenever I take the derivative of something with a y, I just have to remember to multiply by the derivative of y, dy over dx. All right, let's get to it. So x cubed, that derivative is going to be 3x squared. And then to do the derivative of negative xy, I'm going to need to use the product rule. So I'm going to have a box and ribbon here. My factors are going to be negative x and y. Their derivatives are going to be negative 1. Derivative of y is dy over dx. Multiplying that out with the ribbon, I've got minus y minus x dy over dx. And then derivative of y cubed, that's going to be 3y squared dy over dx. Finally, this is going to equal the derivative of 1, which is just going to be 0. So now let me keep all the dy over dx's on one side and move everything else to the other side. So this negative x dy over dx is fine. So is this 3y squared dy over dx. Those can stay. Moving to the other side now, I've got a minus 3x squared that's going over there, along with a y that I'm going to add to get over there. At this point, since I only have dy over dx's on the left side, I can factor that out. So that leaves me with a negative x plus 3y squared in a parentheses over there. And to get the derivative, I just have to isolate dy over dx by dividing both sides by this parentheses. So I end up with negative 3x squared plus y over negative x plus 3y squared.